yeah, Illumina is a very interesting company. I didn't know much about genomics in general and genomic sequencers, but they do like really cool stuff. For example, they can digitalize all your genomic code in a simple sequencer run, like 48 hours. And after that, the most interesting part starts. They can analyze the genomic patterns, and then, for example, they can predict what will happen with you in the future. They can use these results to prescribe a medicine that will personalize medicine that will work for you personally. So it's very cool stuff. A lot of smart people, PhDs, are working on that. But of course, we need to make sure that all our products are secure, because the company who are using our products are highly regulated. It could be like any research organization, big pharma, universities, hospitals. They need to make sure that security is addressed, and that's why we have a team which is called product security, and we are trying to make sure that everything is secure which is coming out of our pipeline. And of course, cryptography and encrypting strong data protection is very important in this regard. So this is not, of course, like all security that we do, but a very important one. The funny thing about this presentation, I submitted it to BSides this spring, and they said, oh, very interesting. And then they said, oh, we have so many like other interesting presentation. And they waitlisted me that they didn't accept it eventually. And then I went to listen to their keynotes, and there were like guys talking about something like their difficulties in relationships with their friends and girlfriends. And I was thinking, why they presenting that at a security conference, right? And I hope that this one will be more interesting and more relevant to the context of this forum. And not, it will not be boring as well. So this is what I'm going to talk about today. I want to touch base on history and business use cases which involve hardware encryption. Why it's important, I just want to position the whole like TPM thing in the context of what other cryptographic methods and what other use cases you can solve using hardware-based encryption. After you understand that, I will go to the use cases related to TPMs and about the architecture and about how TPM can be used to secure data in sensitive cases, like, for example, medical devices that I'm dealing with. So this is actually a solution which comes back to 2003, 2002, maybe more than 20 years ago. And I consider this is like my first engagement with hardware-based encryption. It was in a big credit card company. And arguably, I consider this solution as the most secure in regard of how all these cryptographic materials and assets were protected. So the business use case was as follows. We needed to decrypt, not we, but a third-party processor of credit cards, because credit card companies, they usually like hire a lot of third-party companies to process their transactions coming from their customers. And there was a need at some point to decrypt credit cards, because when files are initially coming to third parties, all these credit cards is encrypted or tokenized. In this case, they were encrypted. But at some point, when they needed to do some kind of research, they needed to be decrypted. So, and the question was how to share in a secure manner these cryptographic keys with our third-party partners so they could decrypt on their side. So for that, we used a setup with Encipher and Trust PCI card, which you see on this picture. The card probably was like a little bit different, but the same idea. It just inserted to PCI bus. And after this is done, you basically need a couple of people out of a set of three. We call it like 2 of 3, right? People with smart cards to unlock it and to make sure that it actually works. This is what's a very good and reliable security control. The other security control, this room where this PC was located was completely locked. There was no any connection, not only to internet, but even to local network. So completely isolated environments and two simple functions that we were performing in that room. So the first one, we could generate this data encrypting key and then encrypt it with key encrypting key. And the second operation, when we needed to share this key with third party, we would print it out on a printer which was in the same room in clear text. Then there was another interesting step that I was not involved to, but I was told that they would take this printed key, split it physically in two parts, and send it in two different envelopes to two different people in third parties. And then those two people would need to get together to construct the whole key again. So that was cool, right? And again, if you look at all this access control, air-gapped room, everything is there. It would be very difficult to compromise to this setup. The only disadvantage, of course, that use cases here are very limited. It's not scalable. You cannot share this solution with all other business units that might need to do encryption or decryption of data. The next one, that was interesting too. So I worked for a big company which was dealing with small business automation, tax preparation, and payments. And they use appliances to protect sensitive PI, payment and tax data, very sensitive data as well. They use in-ring network appliance, and they were performing different kind of creation, crypto materials, encrypting, decrypting. And the most interesting thing that it was not like the previous case. This is network appliance. When you have network appliance, the problem that you need to solve, of course, access, right? How you access to this device, and how you use those keys, how you create those objects. The access was protected by user password based, and of course there are different kind of network controls and OCLs to make sure that it's not easily acceptable. Still, in my case, this solution was not that secure as the previous one, because as soon as you put anything on network, and as soon as you provide access to people, your crypto just as good as your IAM policies, right? If you screwed it up, it doesn't matter what crypto is, because somebody can get access to your keys and do decryption, encryption, whatever. This is a interesting experience as well. Back from enterprise solution to small cryptographic modules as well. They call it modules on a chip. It is a so-called secure element. And Samsung used it in their IoT division to provide root of trust for their devices, IoT devices. And the way how it was implemented, the key which was specific to a device was provisioned at manufacturing state. And we use that key to create a CDSA signature. So when device talks to somebody and attaches the signature to the message, it was very easy to identify the identity of this device, because each device would have its own private key and certificate that were protected by a secure element. The only caveat that I found with this solution was that still to get access to that key, the only thing that you would need to know is some kind of credentials or password that was provided by the manufacturer. So if that password is compromised, then you could extract this key, and after key is extracted, you can pretend that you are this device by creating a CDSA signature with this key. So, but again, The attack vector here is against a single IoT device, not against all devices. So it was like very important to make sure that each IoT device has its own key and its own certificate. Now, even like more interesting case, big payment network where I worked at least like almost 5 years, and they had like very like various business use cases. They could use it to protect sensitive PI, payment data, tokenize credit cards, even create digital signatures for themselves and for their partners. All of that was implemented on backend HSMs, and they like have like literally hundreds of them. The interesting like use case, one interesting use case that I've seen to enable their partners, they even put one HSM hardware security module to internet zone, meaning that the device was directly accessed from internet. All vendors were saying that like it's not a good solution. I was saying that it's not a good solution. Usually you don't put HSM to a zone which is available from internet. But just like in any other companies, there was like a serious business use case, and that solution was allowed to be implemented. The model of access to these devices was like even more comprehensive here. Of course, they had like user-based access, and most importantly, probably for application and services, certificate-based access. Network OCLs were in place. Keys were not exportable in the most cases. And access was integrated with enterprise IAM, such as LDAP or AD. But again, here, like the same like thought here is applicable as in a previous case, that if you just don't address number 5 correctly, if your IAM policies are loose, if your access is not enforced, then again, all this like massive infrastructure doesn't mean much, because if like an attacker has access to crypto materials, they can decrypt all your secrets, they can spoof your signatures and so on and so forth. Okay, let's just move to the next one. Finally, we got to TPM. So now I'm in the world of medical devices, and TPMs are very important in this regard. Why do we need to use them to, and why do we want to utilize a strong hardware-based encryption? The reason number 1 for us is that researchers love finding secrets in config files or in binaries. And when they find something like that, they usually become very loud. They go everywhere, and FDA is watching, of course. And if FDA hears that something is not stored securely, it's like could be like a big issue for them, and it can lead eventually to undesirable for company disclosures. In extreme cases, penalties and fees could be paid. We just like had this case a couple of years ago, and because of internal whistleblower, the company paid like, I think, more than 10 million just to settle one lawsuit. This is a public information, you can find it on the internet. And another bad consequences could be related to delayed shipments of the devices. So all of this like bad consequences. At the same time, if you compare TPM to HSM, economics is very favorable and good here, because TPM modules are available out of the box in all contemporary Intel or AMD based boards. Even like if you don't have it integrated into the board, you can use SPI pins that you can find on many devices, including simple ones like Arduino. You can buy that module, TPM module on Amazon or Walmart, and then integrate it through SPI interfaces, physical interfaces. On this picture, you can see like 3 different types of integration. So SPI integration, this is what I already talked about. It can be soldered on bus directly, or it can be even a part of contemporary Intel platform trusted technology. This is like their definition of CPU, which is bundled with things like TPM, so you don't like even need to have it anywhere else. All TPM 2.0 functionality is already implemented by CPU itself. And this is true for both AMD and Intel architectures. ARM is not doing that, but if you want to use TPM on ARM architecture, you can again use those SPI interfaces to connect to TPM. So now, what kind of security artifacts you want to protect? In my case, this is what we are looking for: passwords for services and live users. And sometimes you need to have them somewhere, because when services talk to each other, they're trying to authenticate, they're trying to talk to IAM system to get a token, JWT token, for example. You do need to have some kind of credentials. And those credentials should be entered in human-less manner. Then, of course, you want to protect web server private keys, and we have a lot of web servers running on our devices. You don't want this to be spoofed. And SSH private keys, there are a lot of communications between services through SSH. Sign-in keys, very often, especially during installation, sign-in keys are created on fly, and they're used, again, in some forms of authentication, so you need to make sure that they're stored securely. Then there is a thing which is application level encryption, and in these cases, we recommend using keys stored in TPM as well. Again, this model, to avoid this researchers' moment when they can find the secrets embedded to your code and then start bragging about it everywhere. And number 6 is very interesting. So sometimes you even need to protect your public key. I can describe this use case. For example, you decide to verify signature for all packages, or for example, all your customers' packages which are signed by Illumina, and then install an instrument through some kind of online, over air, or from USB installation, doesn't matter. How signature is usually verified? You're using public key for that, right? But the question is, if a researcher has access to this device, he can swap this public key with his own public key, and then he create a private key which matches that public key, and then he can modify the package, sign it with his own private key, and the system will take and install this malicious package on the device. So that's why, I'm saying, sometimes you need to consider storing public in TPM as well. And some other artifacts like pins, application authorization tokens, which were issued, JWT issued by our IAM system, PI, PHH. So this is probably the most interesting part of presentation. When I looked at, I thought, look, it's such a small device, should be very simple to deal with. But when I looked at TPM 2.0 architecture and Linux system, I realized that in many ways it's more complex than traditional hardware security modules or HSMs. There are five different items which describe this architecture. You have user space applications, of course. You have system services. You have kernel drivers. You have hardware layer. And finally, you have some files with crypto materials encrypted and stored on host file system. So this is more detailed view of this architecture. And on the bottom, you see some commands which are available out of the box for TPM-enabled system on Linux. And these commands are things like create primary context, I will talk about it, create a key, load a key from context, and encrypt data. And all those like errors that you see shows all the flow, how this process is distributed among different layers of this architecture. On the left, you see user space applications, which can be client apps or some kind CLI tools, like TPM2 tools available on Linux. Then you see system services that I will be talking about them shortly. Then those system services are talking to kernel drivers. And finally, you have hardware layer. And there you can have different kind of TPM modules that I already described, or you can have this hardware functionality implemented directly by CPU. And finally, the last portion of it, host file system. And there you can see different kind of objects like private part, public part, primary context, object context, which could be stored in the files, and then in encrypted forms, of course. And then those files can be used to load crypto materials to TPM and perform cryptographic operations. So the first one, let's just take a closer look. User space application. So you can access TPM functionality through command line, and like you've seen those examples on previous slide, or you can access them from your application directly through APIs. I provided a couple of links here. The first one describes how you can access TPM functionality from Python application. The second one describes how you can access this from Microsoft.NET platform using the Microsoft.TSS framework. There are like other APIs, of course, but practically I used like this too, and that's why I provided this link. The next layer, probably the most interesting and the core of all this architecture, it boils down to so-called access broker and resource manager daemon. This is a typical Linux service which is running under TSS account, and it has like two purposes, two parts. So access brokers is actually like two services combined in one. Access broker serializes all multiple clients when they're trying to access TPM functionality and do some operations like encryption, decryption, by sealing the objects. And the second one, resource management, is used to create cryptographic objects like public, private keys and other objects which are available in TPM2 architecture. Yet another important function of resource management is that it handles approximately in the same way virtual memory for TPM as a virtual memory is implemented on any computing system, right? So we have like hardware memory, which is like very small in TPM case. But like if the number of objects is big, you want to have some kind of virtual memory and offload the objects which are not frequently used. And when you need to perform operation, it will be automatically uploaded again to TPM. Operation will be completed and then it can be offloaded again. So this is yet another important function of resource management. And on the bottom, interesting stuff, even like if you don't have your system enabled with hardware TPM implementation, you can still use some kind of simulation service to do the same. And this parameter, TCTI, this is basically like a library which is used to implement all TPM2 functionality in software, plus it provides some host name and port on which the service will be listening to. So this is very useful when you're trying to debug your applications before you even have hardware to do this stuff. Oops. So the next layer is kernel drivers, and like we have two of them. The first one is for resource management. So basically, like when you want to create, modify, or delete any object stored in TPM using the first one, and the second one is for cryptographic operations. It's worth to say that those devices in default Linux configuration are accessible from TSS account. So the idea here is that you have this access management and access broker and resource management service, which is running under this TSS account. And the same account is used to protect access to kernel drivers and to these two devices which are available on Linux. Hardware layer, already talk about this. So basically you can have this connected through SPI interfaces. You can have it as a part of CPU platform for both AMD and Intel architecture. So you have options here. You just need to check. Usually there are tools that would tell you what exactly you have in Linux. And this is very important as well, because when you think about protecting all these objects in TPM, it's not that simple, because this access model which exists in TPM, it's completely decoupled from IAM, which is available on operating system. And sometimes if you want to have granular kind of permissions for your objects, for example, you want principal A to have access to key A only and principal B to key B only, then probably the best way is to store the three artifacts, which is called context, public part, and private part in files, where private part will be encrypted. And when you need the key, you simply upload it to TPM and then perform cryptographic operations. So this is how you can do granular authorization on different objects which are available in TPM. Otherwise, it's only TSS account that I talked about, and it's probably not sufficient for your needs. Then usually when you create any cryptographic system for your specific use case, for your organization, you need to consider some kind of key hierarchy. You cannot just create primary key and use it for all application services and users. Usually, again, this is just example. I'm not saying that it should be exactly like that in your case, but this is what I was proposing for my organization. On the top of this hierarchy, you have TPM root key. And TPM root key, it's not created by you. It comes from manufacturer. It's unique to TPM, and it's used to encrypt everything which is underneath. The first artifact, the first object that you need to create is primary key. So you can have in TPM 2.0, unlike in TPM 1.2, you can have multiple primary keys, and that's why when primary key is created, there is a context which is stored in a file. Context is not a secret, it's some kind of metadata which describes this key and its handle. So basically this is a reference. So for all consequent operations, if you need access to your primary key, you're just using a primary context file as a reference. And then after primary context and primary key is created, you can create multiple keys for your principals. What I mean by principals, it can be services, applications, users, devices, whatever, right? Whoever needs access to TPM, whoever is require cryptographic services. And what's important here, for each secondary key, you will have when secondary key is created, you will have three files: context, public part, and private part. So for asymmetric cryptography, public part is basically public key. Private part is private key encrypted with primary key. And context is, again, just some metadata. For example, it can store information about access policies. It can store information about session. And it's used during the upload. Because when you need the key, you need to provide the three artifacts. to upload it to TPM. After it's uploaded, you can perform cryptographic operations. So this is how it works in general. Yeah, I already talked about this. This is just some considerations how you protect primary key. It's tricky because if you just create primary key, by default, it's not going to survive reboot. So you need to persist it. Then when you persist it, the question is how you're going to protect it. The most common way is with password, right? But if you protect it with password, the question is where are you going to store that password? It's a kind of very well-known problem in cryptography, chicken and the egg, right? You don't know how to protect the last secret in the chain, right? So that's why I'm saying in my solution, you can use, of course, some kind of obfuscation for that password, some kind of pseudo password, which is generated from some hardware-related artifacts, like host IP address, MAC address, this kind of stuff. This is what I've seen in many companies. But it's not very reliable because eventually it can be reverse engineered and somebody will do the same. So my approach is a little bit different. I'll talk about this in a moment. I would say why don't we pay attention to this artifacts, to secondary keys? And here we have more options, and for each user, for each service, for each applications, you can create its own group or user ID and make sure that these artifacts, for example, are available only for service Z. These artifacts are available for service B, and so on and so forth. So, and if you protect it this way, then you can really achieve a very good granularity of access to your object stored in TPM. And on the bottom, you see a couple of commands that the first one is using this. You see, this is how simple it is to load the secondary key. You just using this 3 artifacts, and you are using the reference to the primary context, which is some kind of handle, and you are done. If you don't have access to these files, then apparently you will not be able to load and use that key. And after it's loaded, encryption, decryption is simple. Here. So this is, again, I don't want to talk too much about this one. It's just a common sense, a sequence of events that need to be happen before you can start using your secondary key for protecting your data. So the first, of course, you create primary context, and at this point, primary context will be stored in a file. Then, again, in my implementation, I would persist this primary key in TPM and create a persistent handler that you've seen in the previous command. That persistent handler will be used in all consequent operations related to handling secondary keys. When you create a data encryption key, you will be using that persistent handler for primary context as a parameter. And after you created secondary keys, you can load it, encrypt or decrypt data, and do it for each key that is required for your cryptographic operations. So so this is I already partially discussed it. There is a problem with this TPM service implementation. It's not really compliant with a common Linux methodology where you can create a policy kit for each service, right? So the way how policy kit works, it operates at dbus level, and it can determine which service operations are allowed and which not, right? For example, if you have some service which is reading or writing data, you can say, okay, this principal can only read data, and this principal can only write data using this policy kit. Here, like at TPM service, you don't have this granularity. You cannot create a policy kit for this TPM2 access broker and resource management service. That's why, again, my approach is to use permissions which are set up on files related to secondary keys to implement fine-grained authorization. And like if you set up all these permissions correctly, then you will have a very good separation of duties between different principles. Yeah, of course, like you can play with this like obfuscation and pseudo passwords, but those approaches are not perfect in my view, and very often it's difficult to support while easy to break. So this is access configuration. Yeah, this is like something that you don't see in HSM, and she can't keep me honest, like if I am wrong here. Did you see PCRs in HSM world? I don't think so. Well, at least like when I worked at Visa, I didn't see those. So like, what is PCRs? This is platform configuration registers, right? So this is basically some kind of storage that you can use to enforce integrity of different important system components. For example, you can say, I want to make sure that my RAMFS image, which is used by Linux to do this initial configuration during the boot, is not modified. So what you do? You create a hash, you store that hash to a specific PCR register, and then you are telling the system, when you boot, please verify the hash. If the value is not correct, stop booting. So this is like the level of integration which is very good for devices with TPM enabled. There are like a couple of dozens of predefined PCRs in Linux, but on top of that, you can create your own if you want to. So it's flexible, and like if you decide to enforce integrity of like any file or any code, you can do it. Yet another like interesting thing about PCR that you can bind your TPM access policies to PCR values. You can say in your policies, if this PCR value is not correct, then stop booting. That's it. It's done. So, and this is like yet another like very good way to enforce integrity of your system. So this is like, I'm not going like to talk in details about all of them, but as you can see, the most of PCRs which are standard in Linux are related to UEFI boot, they're related to firmware code, they're related to firmware configurations and data. You can even enforce integrity of your GPT partition table or secure boot state. What is interesting here, there is like one thing which is called IMA, Integrity Management Architecture. So this is like a thing which is available in Linux. It's number 10 on the slide. And what you can do, why it's like cool, because you basically can define what code, what binaries should be checked on integrity, and for which hashes should be stored. And then at syscall level, at kernel syscall level, before syscall is happening, the integrity of those files is verified, and if it's the PCR value is not correct, the syscall simply will stop and will not happen. We will return some kind of error. And like you see like that even like in user space, you have something defined by default. For example, you can enforce UUID integrity, meaning that, like in Linux, each disk has a like unique ID, right? And it's specific to hardware. So if somebody will swap it to another hard drive, then this verification can fail. So there are a lot of things that like you can do to enforce integrity of your system using this approach. The most standard approach you've probably seen by default, even like if you buy in consumer devices like latest Windows laptops, secure boot is usually enforced. And the way how it's enforced based on the signature. But I think they do some integrity checks as well using TPM, which are incorporated in all systems to make sure that hash of boot images was not changed. Another cool flaw that you've seen in contemporary Windows machine is PIN, right? So you don't need to enter the password, long password, you just enter PIN. It's like works in conjunctions with TPM as well, because that PIN's hash is used to unlock the key, which is specific to that particular user. And then exchanges happening between different Microsoft components. One component is sending some random number signed with this key. Another component verifies that signature is correct. And if this is happening, then like your like Windows laptop gets unlocked, and without like need of entering a long password. So you've seen this functionality, but you probably didn't think that it's bound to TPM. It is, and like you can like research it more, and you will see like a very complicated flaw that Microsoft has implemented. It's not completely like open standard. Everything is private, but they do mention that whatever they implement, it's based on FIDO2 standard. So this payload of the messages which get signed and verified, they like are coming from the standard, but again, Microsoft close details how it works. So this is like conclusions and problems to solve. So like as you see, like TPM, of course, like not a powerful network device, right? So no, like I'm not going to argue about that. But like if you look at capabilities, but they're like very similar, right? And some features like PCRs are unique and can be used to enforce integrity of your devices, especially when devices like are very sensitive, like medical devices. Architecture, as you've seen, is not trivial. But if you just like spend some time, it's like easy to understand what it is and how to use it to implement your strong hardware-based data protection. Hardening access to TPM objects is a little bit tricky, and you need to be inventive. I describe the scheme where access is based on permissions assigned to secondary key artifacts, but you might want to come up with something else. I don't know. Key hierarchy, again, the example that I showed is just that, examples that I use, but like in your specific case, for your specific organization, you might need to come up with something more complex or something simpler, I don't know, but do not use your primary context and primary key to encrypt everything. That would be like a very bad decision. Again, yet another point, a good practice would be to identify all principals in your systems, like services, applications, user devices, and what's not, and to make sure that each of them has access to its own key to perform cryptographic operations. This way you achieve like a very good separation of principles method. System integrity, cool thing, already talked about this. You should choose, this is like number 8 is interesting. This is actually like I spend the most of the time with our development teams. So like what is important, what is not important, what we need to protect. It's all about collaboration with your product teams. You like really need to sit down and to understand, is it important, and ask a simple question. If we don't do it, how are you going to store it? If you store it if you bake it to the code, if you put it to configuration file, how easy it will be for pen tester researchers to find those artifacts. If the answer it is easy, then do consider do something more complex than just storing them on a file system. Protection for primary context, again, I explained the problem. If you want to use like what they call ownership, meaning that you would need to have owner's credentials to unlock it, then the question is where you're going to store those credentials. So either you do that, or you just persist your primary context and then enforce access to secondary keys through file permissions. And finally, like whatever you do, very often researchers are just like unpacking your code to see where encryption logic is concentrated, and then just mimic it, right? So instead of like uncovering keys, they can see what part of your application is actually doing encryption decryption, right? So if they see this like logic with all like key-related attributes and parameters, they can do it not inside of your application, but outside of your application. If they have like proper access rights, of course. And then the good recommendation in this regard would be to make sure that your code is obfuscated. And it just will increase attack complexity related to all those reverse engineering efforts. So that's, I think that's all I wanted to talk about today. This is like where you can find me, and LinkedIn or Twitter will be glad to answer your questions offline, or if you have anything online, shoot them now. Thank you. Have a question? Yeah, go ahead.
I wonder if you could look into the crystal ball, looking at all the historical knowledge you have, see how do you see post-quantum cryptography and TPMs and HSMs lining up?
It's like a very good questions, and I attended like 5 years ago. I will ask Shrikant this question again. He knows more than me. But like 5 years ago, I attended a lot of conferences. I listened to all the smart guys from big companies like Microsoft and others who like really advanced in post-quantum cryptography. Microsoft, if you don't know, they built this in the water data center, right? They have like the huge like barrel. They put data center there and then put it to the water, right? You've seen it probably. This is like in-sea data centers. And this data center connected by a cable with some main computer somewhere, right? And this cable, of course, like transmits a lot of data. And they told me like 5 years ago that they already implemented post-quantum algorithm for that kind of transmission of data. But in general, I didn't like, even in big, like highly regulated company, I didn't have like too much appetite to do anything in this regard. So like, and again, 5 years ago, the people were saying to break like major algorithms, especially like asymmetric, it would require some investment similar to Manhattan Project, right? So big investment, but not very big, right? And since then, I didn't have like too many changes because people just think that it's like far away. Researchers are saying it's not. It will happen eventually. If you look at NIST, they are trying to adopt some standards which are resilient to post-quantum, but I didn't see the strong adoption of those standards by companies. This is what my problem. I don't know why, but inertia, people don't understand the threats, but this is where we are. Shrikant, am I wrong?
So we can put windows for the roadmap.
Right?
Yeah.
Those quantum keys kind of rather large.
Yeah.
That's one of the things slowing it down. Everybody likes their speed, but those quantum algorithms are a lot slower.
Yeah, but this is an interesting thing that I took from this presentation that I attended with all these big researchers. They were saying it's not about changing everything to new algorithms. It's like building your crypto infrastructure in such a way that you can switch crypto algorithm easily. And this is what Microsoft was doing. They were saying okay, we're building some kind of framework, and in this all user space applications are going to call crypto through this framework, right? And how this framework is implemented is flexible. For example, today they don't have capacity to change completely to post-quantum, so they use whatever they use now. But tomorrow, when those algorithms are finally approved by NIST and pushed to everyone, the switch to the new ones would be easy. I think this is approach, very reasonable approach. So instead of calling this crypto primitives directly through low-level APIs, create something higher level, right? And after that, you can operate what's inside that framework, right? And when you need to switch, you don't need to change all your thousand of user space application. You're just changing your framework, and then suddenly you're ready for post-quantum. I was trying to implement something like that in Visa, but with very variable. I called it data protection abstraction layer, default. But, and we even had some kind of pilot, but I don't believe it went too far. So, inertia. Any other questions? No? Okay, thank you for coming, everyone.